Hi, folks. Hi
Hello,
again.
hello.
Yes.
Hi, Isaac. Are you the host?
I believe
so nice to
Jeva
see you.
is. Yeah.
Alvin Hall.
So, Jeba, can you give the five of us co-host status, please?
Yes, sir.
Thank you.
Sorry about the mix up. This is a wrong
Yeah, we need to
Zoom
get
link.
a little together. So, if you can make us make the five of us hosts, that would be nice.
I will.
Who's missing? Anvesh. Anvesh, turn on your camera so I can introduce you all. Anvesh, turn on your camera. Yeah.
Yeah, sorry.
Yeah.
I thought something was wrong and I tried to reset everything.
So let's see. Co-host is Farrokh. Anvesh is going to be co-host. So while we are waiting, I have a question. Who's going to start from ASME? Who's going to introduce the session? Isaac?
Isaac will.
Yeah.
And
yeah,
Isaac
he's
will
gonna
also
follow.
end it. So if you can turn it over to him at the end.
And you will do it at the end also, Isaac?
Yeah, I can close this out whenever you guys are finished. I would assume, like you said, you've had a couple run-throughs on this.
Yes.
So yeah, I mean, there's no problem there. I don't plan to be super long-winded on it, but
So lovely to see you, Pedro. So Siavash, Isaac will open and pass it on to you. And then at the end, you pass it back to Isaac.
Sure.
So we'd like to introduce our people. Pejman, do introduce yourself. He's a professor here in mechanical engineering.
But do you want to hold off till 6
So just
o'clock?
let me know. So I think it's okay. And my name is Pejman Kazanpur. I'm actually an associate professor in the School of Aerospace and Mechanical Engineering. I'm working on energy system, especially electrochemical energy system, and try to kind of achieve sustainability through integrating of such system.
And Pejman is heavily involved in oil and gas. He comes from Baker Hughes, and he's heavily involved in oil and gas. So now, Sarah, introduce yourself. Sarah has something special. She's Pejman's wife, and so we work together.
Hello, everyone. So good to see all of you here. My name is Sara Hajihashemi, a PhD student in the School of Industrial and Systems Engineering, working with Professor Allen and Professor Mistree also. And we are working on designing the satisficing framework to be able to predict the behavior of the future of the system in any kind of the domain, not specific to a specific domain. And as Farrokh mentioned, I am Pejman's wife.
Okay. So, Shadi, go ahead, introduce yourself.
Hello, everyone. My name is Shadi. I am a PhD student at Industrial and System Engineering. I worked with Dr. Rahman now, and but my previous professor, Dr. Kazanpur, and I am so glad to joining to your groups, and I am very glad to hear some lectures from my friends. Thank you.
So our previous chair of the graduate student community is Roshan. Roshan, do introduce yourself and let them know about what you're looking for.
Hi everyone, my name is Roshan and I'm a PhD candidate in the School of Aerospace and Mechanical Engineering. Funny enough, I know Isaac, he was my solid mechanics student in the junior year, so nice to see you, Isaac. And yeah, good to see you all. And I see some familiar faces. Jeva sir is here as well. And so, I mean, for the people who are new to the lightning talks, I think hopefully this format is something nicer, and we always try to have different themes. And what better theme than AI and just understanding how it is applied in real sciences and how it can be applicable in the industry. So hopefully this is a good, hopefully this is a talk where some collaborations happen, some bigger things happen. So hoping for the best. Yeah.
Great. Rodney is the current co-chair. So Rodney, do introduce yourself.
Yeah, hi everyone. My name is Rodney. I'm a PhD student now here at OU. I got my master's a few years ago, worked in industry for a couple of years, and came back for my PhD. So I work with Dr. Song in the Building Energy Efficiency Lab. And like Professor Mistree said, I'm one of the co-chairs of the GSC this year. And I'm really excited for these lightning talks. Like Roshan said, AI can be a really good tool if it's used properly. And I'm really happy that the ASME Central Oklahoma chapter is willing to keep hosting these lightning talks with us.
Samuel is the current co-chair. He's from electrical engineering.
Hi everyone, my name is Samuel. I am in the School of Electrical and Computer Engineering. I am one of the co-chairs this year. I work with Dr. Sigmarsson at the Advanced Radar Research Center. And I look forward to this event. This is a great opportunity to learn new things. And even though some of the presentations are not from your specific discipline, it's amazing to see how these technologies, in this case, artificial intelligence, is applied in different disciplines. So it's going to be an exciting event.
Thank you. There's another wife who may like to introduce herself, Janet Allen.
Hi. So I'm a professor in industrial and systems engineering, and I also happen to be married to Farrokh. We've been talking and thinking a lot about AI, and I look forward to what the students have to share today.
And Janet is a fellow of ASME. So, Suramya, go ahead.
Hi everyone, I'm Suramya Sarkar and I'm in my second year and I'm working with Professor Farrokh Mistree and Professor Janet Allen in Industrial and Systems Engineering. I'm working in context-aware specific control and systems in rural areas, and it's nice to be here and I'm really excited for today's lightning talk. Thank you.
Yes. So, Jeva, would you like to introduce your team?
Yes. Isaac, you go first.
Yeah, no problem. So my name's Isaac Stovall. I'm the current ASME chair for the Central Oklahoma section. I graduated from OU actually in 2023 in May, and I currently work for Halliburton in Duncan, Oklahoma, working on surface equipment and all sorts of things like that. And yeah, we're very excited to hear about what the students at OU have to think about AI. It's a hot topic. And then I think moving forward from that, I think Ed Laverdure is on if he wants to take over next.
Okay. Ed Laverdure, I'm the vice chair in ASME, and I am the interim chair in the reboot of the professional section for AIAA. And there'll be more to follow on that over the course of the next month. I am from the operational side with my background in the Air Force, and I am a humble student of AI, learning this. So I am very much looking forward to hearing what you all are working on.
Who's next from the SME side?
Yeah,
John.
John Heaton's here, I guess.
I'm John Heaton. I'm a mechanical engineer, retired from Halliburton Energy Services, and currently the secretary for the Central Oklahoma section of the ASME.
Larry.
Yeah, can you hear me?
Yes.
Okay, I'm Larry Hobrock. I'm a retired chair and professor of mechanical and aerospace engineering at OSU and former vice president of ASME Systems and Design Group. And I've had worked for 3 different companies in addition to my academic career. So I sort of understand mechanical and aerospace engineering from both the industry side and the academic side.
My name is Jabbar Asir. I was one of the past chairs of ASME, been a member for a long time. I work for an A&E firm in Oklahoma City, Guernsey and Company, and we are an architectural engineering and design firm. Looking forward to this presentation. Always enjoyed the past presentation. So you have a high standard that you have set to yourselves.
Yeah, and then I think I see, is John McCashron on?
Yes, I'm on.
Oh, perfect.
Can you hear me?
Yes, sir.
Oops, I tried to turn my video on. Who knows what I'm gonna look like. So John McCatron, I'm the current treasurer, been treasurer actually for a long time. Mechanical engineer at the FAA, working on the Customs Border Protection surveillance equipment.
And I think the last one I see on here is Nathan.
Good evening, everyone. Nathan Weber, currently work at Continental Resources. It's an upstream oil and gas company in Oklahoma City.
Great. From our side, we have Gulnaz, who's a professor in computer science. Go ahead, Gulnaz. Do introduce yourself.
Hi, everyone. This is Gulnaz Habibi. I am assistant professor in Department of Computer Science from University of Oklahoma. Nice to meet you all.
Why don't you tell them what you are working on? I think that's a very interesting area, the way you're using AI and stuff like that. Go ahead, Gulnaz. Gulnaz?
So I'm doing a multidisciplinary in different areas from robotics and machine learning and multi-agent systems. So I'm working on robotics basically, but more on computer vision and how we do the multi-agent systems. So we connected vehicles and, integration of the aerial vehicles and ground vehicles.
Great. Avinash?
Hi everyone, I'm Avinash. I'm a PhD candidate in the School of Aerospace and Mechanical Engineering. I'm doing my research with Dr. Jitesh Garg on energy storage materials, and I'm also a part of the GSC leadership team. Excited for the talk.
Zain.
Hello everyone, I'm Zain Tasneem. I'm a PhD student in the School of Aerospace and Mechanical Engineering. My advisors are Dr. Pejman Kazimpur and Dr. Iman Gamarian. I'm working in predicting the behavior of fuel cell using machine learning. I'm also a member of GSC leadership team.
Shiva.
Hi everyone, this is Siavash Mandegari. I'm a second-year master's student in Industrial and Systems Engineering. I'm working with Professors Janet Allen and Professor Farrokh Mistree. In my master thesis, my focus on developing a computational framework, which is based on a large language model to generate business plan for entrepreneurs and policymakers.
Thank you. Wonu, do introduce yourself.
Hi, my name is Wanu. I'm a PhD student with the AME department. I'm working on using machine learning models and AI in robotics and battery systems.
Great. Anshu.
Yeah, hello everyone. My name is Anshu Raj and I'm working with Dr. Suzy Zhu. I'm also in aerospace and mechanical engineering department. And I'm working on molecular dynamics, CPFEM, which is crystal plasticity finite element method, and using LLM in material science, and also started using machine learning for the material science projects. Yeah, thank you.
I think we should be ready to start, Isaac. And the request we have is if you could record this talk because you would like to upload it to the GSC YouTube channel.
Yeah, I believe it is. Is it recording?
I think, Dr. Mistree, are you recording? I gave permission.
This is just taking notes. It's not recording it. So you need to record via Zoom or give me permission to record it and I will record it via Zoom, my Zoom.
Yeah, either way is fine. So
why don't you record?
It is recording.
Okay.
Okay.
Yeah, it is recording. I will send you the link later on after it's done.
Perfect. All right. Well, let's get it started then. So yeah, obviously we're very grateful that you guys are including us on this and that we're able to bring you guys in and have a joint meeting here. This is our October technical program, so we're excited to hear about it. And like I said earlier, what OU's got to talk about using AI in the industry and what applications we can have. We're just excited to hear about from the students. That's really what I've got to say here. Obviously, we're representing the ASME Central Oklahoma section. So as you guys move out into the workplace, if you end up staying in Oklahoma, be sure to give us a shout and stay connected. But other than that, I think I can hand it off to Siavash. Are you the one that's going to be moderating the panel?
Yes, sure. Thank you so much, Isaac.
Yes, perfect.
Okay. Good evening, everyone, and welcome to the ASME GSC-GCOE Lightning Talk. I am Siavash Mandegari, PhD candidate in Industrial and System Engineering at the University of Oklahoma and working with Professor Janet Allen and Farrokh Mistree, and I will be moderator for today's session. First of all, I truly appreciate ASME leadership team for providing the opportunity for us to present today. Our theme this year is AI in engineering, where we will explore how artificial intelligence is transforming research across disciplines, from industrial engineering to mechanical engineering and computer science. We have an exciting set of talks ahead that highlight how AI is helping us to design, predict, and innovate in complex systems. Here is a quick overview of today's agenda. First, we will begin with presentations by our panelists, each sharing their research, and altogether the 3 talks will take about 40 minutes. After that, we will have a 10-minute response session where the audience can reply to the questions that each presenter poses at the end of their talk. And finally, we will open a 10-minute Q&A session where participants can ask questions to any of the presenters. So since we will be collecting questions until the end, I encourage everyone to note your questions as you listen to each of the panelists. Now, let me briefly introduce our 3 speakers for today. First, Sara Hajihashemi, PhD student in the School of Industrial and System Engineering, will present predictive analytics across domains, managing complex spatio-temporal datasets. Sara's work focuses on using transformer-based predictive analytics to forecast evolving systems across different engineering applications. Next, Shayan Shafaei, PhD candidate in the School of Computer Science, will present increasing compressed KNN efficiency for faster patient diagnosis. His research highlights how compressed KNN model can be accelerated for faster and more accurate patient diagnosis using randomized learning. Finally, Anvesh Nathani, PhD candidate in the School of Aerospace and Mechanical Engineering, will share his research titled Accelerating Materials Structure Identification with Deep Learning. His study applies AI-driven models to turn diffraction patterns into immediate and actionable material insight. Together, their talks represent a broad view of how AI connects industrial engineering, materials engineering, and computer science. And now, to begin our session, please join me inviting and welcoming Sara Hajihashemi, our first presenter.
Thank you so much, Siavash. Hello, everyone. My name is Sara Hajihashemi, a PhD student in the School of Industrial and Systems Engineering, and I am working with Professor Allen and Professor Mistree. And today I want to talk about our recent work, which is predictive analytics across different domains, managing complex spatial temporal data set, and using supply chain as a test example. Before going through the whole presentation, let me to say why we are going through this problem and what we wanted to get end of the presentation. Why predictive analytics is needed in evolving system. In any modern system, that doesn't matter, is belong to supply chain, energy network, oil and gas operation, or healthcare services, this kind of the system continuously change in its structure, demand, and external condition. So predicting the behavior of the system for future is really essential, since we need to know the behavior of the system in the future. But traditional model fail when past data no longer reflect new conditions. So in this, what kind of the common challenges across all these domains that I mentioned? In any domain that you are working on it, as I mentioned, you are in supply chain, you are in healthcare, energy, oil and gas, you are dealing with different type of the data set that might has this kind of the feature. With feature, high variance data set that is from low number to really high number that are not outlier or valid number, part of the data, or data that might change based on the time and based on the geographic. So also, the data might be heterogeneous. That means combining physical, social, and economic layers means a complex data set. So evolving trends requiring a scalable model that adapt over time without manual segmentation. To apply our test, we use the supply chain example, and we come up with the data from Puerto Rico from 2005 to 2013 and predict the 2015 data. What kind of the data set? As I mentioned, two different data sets. One of them is a high variance data from almost 0 to 90,000, and another data set is 9 years geothermal temporal grids. We notice that the transformer model outperforms all other models. So at the end, we noticed that transformer model achieved the best accuracy for complex high variance data. And the most important things, capture temporal and contextual pattern. When condition shift, data might shift. So this result is applicable across different domains such as energy, oil and gas, healthcare, and supply chain. So let's get to the detail of the problem statement. Such a system, such as all the domain that I mentioned, continuously will change based on the structure, demand, and context. So forecasting is critical for planning and resource allocation, but difficult as system and condition evolve, as system change. So the data that we want to predict, the data that we are dealing in these domains might have variety range of the data from almost 0 to really high number that they are not outlier or valid number. The data might be temporal variation, or this one is the map of Puerto Rico. You see the data might be belong to different part of the places, and also based on the geographic might change based on the time, based on the situation. So traditional model assume a stable pattern. Such assumption fail when system change dynamically, continuously. For planning in supply chain, infrastructure planning, energy, healthcare, and other domain. So now I mentioned, okay, what is the problem that we are dealing with the data that could be any domain. Now let's move toward our test example. In our test example, we are dealing with two different data sets. One of them is from low number, has a high variance data from almost 0 to 90,000, which is number of the customer in different areas. Some of them is rural area, but some of them is crowded city like capital city. Or the other data set that I am working with it is high complex data, high dimensional for 9 years, data is changing based on the geographic and temporal variation. So traditional tool require lots of manual segmentation, pre-processing, which add complexity. And the main things we might cause to lost part of our data, cut part of our data that is not outlier is part of our data. So we are looking for a model that be able to handle irregular data and the data that is changing based on the geography, based on the time, and also complex data sets. So we went through the data preparation, absolutely. Main important things having the data. We got our data from World Population Data website, and we got data from 2005 to 2013 and implemented in GitHub Green Supply Chain GitHub, because we wanted to get the output. What was the output? Customer size and connect cost, the two different data sets that I mentioned. But to ensure that we have consistently, we went through lots of economic adjustment, changing the fuel, electricity, and all this stuff. And finally, we got our two data set that already mentioned, one of them high variance, complex, for connecting the customer to the different store, and one of them showing the size of customer in different area of Puerto Rico. So we implement different kind of the method to these two data set. We went through the linear regression, polynomial regression, random forest, XGBoost, but we were not able to get a good result. Finally, we went through the hybrid, mixed two of these, random forest and XGBoost. We were able to get the good result from this hybrid model, but we went through lots of manual segmentation, pre-processing, and kind of adding complexity to the model. So we tried another model, which is transformer model. What is transformer? Most of you are familiar with it because the name of transformer even is in ChatGPT. A deep learning architecture introduced in 2017 for sequence modeling. It captured temporal dependency and contextual relationship directly from data, enabling segmentation-free forecasting for dynamic and complex system. So here I add the feature that are important in transformer, and it helped us to come up with one single model without any manual segmentation for our demand forecasting. One thing is we were able to easily fit the data for 2005 to 2013 all at the same time. We didn't need to go through any manual pre-processing. One important feature that it has, for example, in our year in 2008, Puerto Rico had inflation crisis, or in 2011, they had field shift. What transformer do? Transformer assign the weight to the important years. That means it's telling to the model, pay attention, these years are important. You have to get all these shifts that might happen in the data. And finally, we were able to deal with all this in only one single model. So to show you the result, we went through MAE and RMSE to see how far our prediction is from the actual data that you are familiar with them. And as you see, all the model that we implement, finally, those are, we didn't get the good result, but we get the good result from hybrid model. But in MAE, but in RMSE, it was not a robust solution that you see, the difference between MAE and RMSE. But in general, we were able to get a good result for both data set. Customer size and connect size is kind of, as you see, also robust solution that transformer gave it to us. So we wanted to say, someone said, okay, that's kind of only the number. No, we want to show our result statistically is correct. So we went through the different kind of the test, paired t-test and Wilcoxon test. So we consider, okay, which one, MAE and RMSE, which one is normal distributed, which one not. So based on that, we select our test. And finally, based on the p-value, we noticed that MAE is significantly better for the transformer model. In RMSE is not statistically better, but even it looks better in the numbers that we see. So, as a closing remark, as we mentioned, the transformer model achieved the best forecasting accuracy for high variance spatial temporal data without any manual segmentation. And the most important thing is it captured temporal and contextual pattern based on the feature that the transformer has, based on the ability to assign the weight to the important years, so enabling generalization under shifting and uncertain condition, and we are able to at least partially do the prediction if the data changing. So we used supply chain as an example, but doesn't matter. It's applicable in any kind of the domain, oil and gas, energy, healthcare, because in this kind of the system, we are dealing with this shape of the data set as well. So we are going forward with this kind of the study, and we want to answer two questions. How can forecasting outputs be connected with satisficing logic to support decision under uncertainty? Or how can predictive analytics and satisficing framework be combined to enable adaptive system design? We would love to hear from you in your experience. It doesn't matter in any domain that you are working, energy, oil and gas, supply chain, healthcare. What factor or disruption most affect forecasting accuracy, such as demand fluctuations, supply instability, or policy changes? So another question is, we would like to hear, how could the transformer-based forecasting approach be tailored to help your industry better manage uncertainty and plan for sudden changes? Thank you so much for listening. And now I invite Shayan Shafaei to share his thought on increasing compressed KNN efficiency for faster patient diagnosis.
Thank you, Sarah. Hello, everyone. My name is Shayan Shafaei. I'm a PhD candidate in School of the Computer Science at the University of Oklahoma. Today, I'm going to present our latest research, which is about the increasing the compressed KNN efficiency for faster patient diagnosis. And also my advisor is Dr. Chao Lan. These days, the healthcare
Excuse me,
system.
Shayan. Sorry if I disturb you. You may change your screen.
Okay, sorry. Just a moment. Let me share that again with you. Do you have my screen?
Yes, and go to presentation mode, please. Yes, that's right. Okay, go ahead.
Okay, where is the... Okay. These days, the healthcare system have a vast number of the patient records, and to analyze this data efficiently, they rely on the machine learning models. Among the different machine learning models, the KNN or K-nearest neighbors model is one of the most powerful and widely used method in this area. But the KNN faces two main challenges. The first one is that it is memory inefficient, and the second one is that it is computationally heavy, especially for the large scale data set. Therefore, to tackle this limitation, lots of compressed KNN methods have been proposed to compress the training data. And one of the state-of-the-art proposed method is the weighted nearest neighbor or WNN method. This method is very effective to compress the data, but the main disadvantage of WNN is that the compression process of that is too slow. The limitation of WNN motivated us to propose the variant of the weighted nearest neighbor, which called the randomized weighted nearest neighbor. And the main goal is that to accelerate that while preserving the accuracy. And the idea of our proposed method is that it's very simple. We just replace the random selection with the greedy heuristic search, which using the weighted nearest neighbor, and that's very expensive. especially in the large scale data set. And at the end, to evaluate the performance of our method, we use the different real world data set in the different scales. Machine learning is an essential part of the modern healthcare, since it helps to make faster and accurate diagnoses with keeping the process efficient and affordable. Among the learning model, the KNN algorithm is widely used. Since it's interpretable, which means the decisions are easy to explain, and also this method is accurate for the clinical data. The other advantage of this method is that it is simple and easy to implement, since it doesn't have any training phase. So this makes the KNN a strong and reliable baseline for the early decision detection in the healthcare system. But how does the KNN work? The mechanism of that is very simple and straightforward. To have a better idea, I provide an example in the right-hand side, and every point represents a patient. And we have a new patient which shown with the X here, and we want to classify that and predict, for instance, is it diabetic or non-diabetic? We try to diagnose that. When we want to use the KNN is going to measure the similarity between the new points and all of the other patients in the data set. And after that, select the K most similar patients to our new points. And here we set the K to 3, so that's select the 3 most similar patients. After that, the selected patient vote, and the majority class becomes the final prediction. In this specific example, since 2 out of the 3 classes from the green class, so the final prediction is green for the new patient. But what's the limitation of that? As we can see, for every new patient, we have to measure the distance between that and every other patient. So it's computationally heavy. Imagine that on the large scale data set, which has a million data set. Also, it doesn't use the memory in an efficient way, since we have to store all of the patients. So to tackle this limitation, one of the proposed method, which is very strong, is the weighted nearest neighbor, or WNN. The goal of this method is to pick a compressed subset from the training set, compressed weighted subset from the training set, and the weight of each sample in the compressed set reflect the level of importance of them in the final prediction. This algorithm has a main loop, and to have a better idea, I'm going to explain each step with using the example in the right-hand side. In this method, for each point, in the first step, it tried to measure, to find the nearest point from the opposite class, which will be the radius of the homogeneous ball. What's the meaning of the homogeneous ball or the pure ball? Is that it tried to find the ball which cover the samples from the same class. And it's going to do that for all of the points. And after that, it selects the largest ball. The largest ball is the ball which covers the most similar points. In this specific example, as we can see, the ball which is centered at A is cover more samples in compared with the ball centered at the B. So the WNN pick this ball and add the center of that, which is the A, to the compressed set, and also add the radius of that as a RA, which represent the weight of that point. And after that, all of the covered points will be removed in the updated training points. And in each iteration, it tries to find the largest ball again. So as we can see, since the mechanism which uses the greedy heuristic search, so that can be very expensive on the large scale data set. This limitation motivated us to introduce a variant version of the weighted nearest neighbor as a randomized weighted nearest neighbor to accelerate the compress process while preserving the accuracy with just a little loss in the accuracy. And the idea of that is very simple. Rather than we are going to pick the largest ball every time, in this method, we are going to pick a point randomly and define the homogeneous ball of that homogeneous ball with center at that point, add the point to the compressed set, and remove the ball. So it causes to have the lower cost, and it can be used on the large scale data set. To evaluate the performance of our data set, we use the 5 real world data sets in the different scales. As we can see in the right-hand side, it shows the error versus the different data set, and the smaller number means the better performance since the y versus is error. And as we can see in the most of the case, the performance of the RWNN is very close to the weighted nearest neighbor. And another interesting point is that in some cases like AIDS dataset, the randomized weighted nearest neighbor can achieve the higher accuracy in compared with the traditional KNN. And also we use a large data set, which is a diabetic. As you can see here, we don't report the value of the weighted nearest neighbor here since it couldn't run that in a reasonable time. It takes roughly 1 or 2 months to find the compression set. In the left-hand side, we compare the compression time of KNN of the weighted nearest neighbor and randomized weighted nearest neighbor. And as we can see, the randomized weighted nearest neighbor is roughly 100 times faster than the weighted nearest neighbor. And for the both of the methods, since for the classification based on the compressed method, compressed set, they use the same method, the inference time or the classification time is the same, and that's much faster than the traditional KNN. At the end, in the summary, we propose a new variant of the weighted nearest neighbor, which is significantly accelerates the weighted nearest neighbor only with a minor loss in the accuracy. And RWNN ineffective in handling to the large scale data set, and it can be very useful in the healthcare system since the prediction of that can be very close to the real time. And as a following research, since the current version of the WNN and RWNN, both of them just adopted when k is equal to the 1. So we try to develop that, which is working effectively for the different values of the k. And also we try to find an other variant of the RWNN, which is generate the multiple compressed subset rather than the single compressed subset, since we believe that it can increase the accuracy and achieve the better accuracy in compared with the current model. At the end, I would be happy to discuss or join any available projects on the developing machine learning algorithm or applications where our method could be applied. Now I inviting the Anvesh Nathani to share his thoughts about the accelerating materials structures identification with deep learning.
Thanks, Shayan. I'm Anvesh Nathani. I'm PhD student in aerospace and mechanical engineering. My PhD advisor is Dr. Iman Gamarian. Today, as part of ASME Central Oklahoma lightning talk on AI in engineering, I'll show how we are accelerating material structure identification with deep learning. This work is collaboration with Accelerated Material Development Laboratory at University of Oklahoma and Dr. Kolinoff's group at Stanford University, where we focus on how we can find out the ability of deep learning to analyze nanobeam electron diffraction at scale. Let me give you a quick overview. So I will start with background on diffraction and how 4D STEM became prominent technique for understanding materials, particularly nanomaterials, and the challenges we will face when we have hundreds of thousands of diffraction patterns with random orientations and thickness. To address this challenge, then I'll discuss how we address this challenge with data-driven deep learning method, where we developed a data set and applied graph-based attention learning. Finally, I'll close with how our model performed in terms of accuracy, speed, scalability, and reliability. Then I'll close with our research questions and inviting collaborations. So if you see, for diffraction, the entire talk will surround around diffraction, particularly electron diffraction. So you can think of electron diffraction as 2D fingerprint of 3D arrangement of material. For a crystal material, if you pass an electron beam, it will produce a discrete patterns where we call each discrete spots on a pattern, where each spot we call black spot, and we get a pattern. And yeah, for 4D STEM, we produce hundreds of thousands of these patterns at each scan position, which are like extremely hard to process. And other challenges, if you have complex material, heterogeneous material like gadolinium titanate, we can go from single crystal to amorphous from left to right. As you see, we'll go from very sharp spotted patterns to complex noisy patterns and halo rings for amorphous. How we are processing this data? Currently using template matching techniques. To simply emphasize, template matching is where we have millions of diffraction patterns. Already known patterns will be matched against the experimental patterns or simulated patterns. So if you have very clear spots like here, it's very easy to process. You will get 75% accuracy. As you increase thickness, the patterns become extremely noisy because of multiple scattering effects. And if you change orientation, the same complexity arrays in the data. So the accuracy drops way low. Another challenge is matching hundreds of thousands of patterns against millions. For each pattern will take a lot of time. It's a tedious process. So this bottleneck motivated us for data-driven method, where we develop a data set with 38,000 real materials in the diffraction materials project database for 100 thickness levels and 100 random orientations. We ended up with 350 million diffraction patterns. Then how we process these diffraction patterns? So instead of using the diffraction image, we use the spots as a set of triplets, where it represents two-dimensional positions in polar coordinates and intensities to limit the pixel noise, to eliminate the pixel noise. Then we process this into a deep learning method encoder, where we change the dimensions from 3D to higher dimension using a lot of parameterized layers, multiple layers, and from width and depth. So finally, we'll end up with a higher dimensional latent representations, which can represent millions of patterns in much more generalized way. Then how we extract the relation from these embeddings for each spot across each spot, different spots. So there we used an attention graph generator. It works on principle of attention. You can think of attention as a simple cosine similarity matrix, but it's learnable and weighted. If two spots are extremely related, we'll get more weight and model will learn through the learning while training. So inside attention layer, we have some other features where in each attention, we can have multiple heads where it sees entire diffraction pattern from different views, which will be averaged. And we'll have then we have a depth. Depth is like we redefine those interactions by learning the embeddings. Finally, we average and aggregate our attention matrices into our attention graph, which is a dynamic learnable pairwise relationships. For a set of n spots, you'll end up with n cross n matrix where each row represents how much particular spot is relevant to each other spots. That is our weight. Then once we have the attention graph, we will pass this graph matrix into our transformer encoder attention layer as a bias where we extract node degree, shortest path distance, and edge-weighted shortest path distance into our attention bias, and our centrality will go along with our embeddings. So this attention layer in our transformer encoder produces very rich representations. For this purpose, we used mixture of experts. In general, we'll have a single expert here, which won't be able to capture the rich future space spanned across diverse data set. For this purpose, we introduced mixture of experts. I'll simply refer it as MOE. So where each embedding dimension will choose its particular set of experts based on the threshold we'll set. If we set K2, it will choose any of the 2 experts relevant to it and keep the rest of the experts idle. So in this way, we can increase the model size without model capacity, without increasing computation. So finally, we'll end up with very accurate crystals classifications where so coming to the performance of the model, we have very accurate, fast, reliable. So I'll go one by one. So in terms of accuracy, if you see against random forest, our model improved by 13 points. We achieved almost 70% accuracy on single patterns. Apart from that, if you go from cubic to triclinic, where symmetry decreases, so cubic patterns are extremely rich in data. So here we will have same accuracy for our model. Very simple acronym is GMOE. Against random forest for cubic, it's same. But as you go towards complexity, where we have less samples and much more complex data, our model performed 100% better than the random forest for the cases of lower symmetry. So our test data set spans 1 million patterns from 10,000 real materials. So you can think of it like each % of improvement is like classifying 10,000 patterns accurately. And it's coming to the fast, it can process like 10,000 samples in less than a minute on single device. For reliability, I'm showing you the 4D stem scan experiment of gold nanoparticles. This is a dark field image. You can think of each spot, bright spot will be a diffraction pattern. If you do 4D stem experiment, we'll end up with 60,000 patterns. But in general, most of them are very noisy and redundant. Still, our model is able to capture, analyze those noisy patterns, which are redundant for like traditional methods. And here we reduce time from hours to minutes and without any processing. So finally, I'll close with, we ended up with a quick, reliable crystal predictions, reducing analysis time and less manual work, less pre-processing, post-processing, and more speed for new materials for batteries, chips, alloys, and nanotech. it fits into current transmission electron microscopy workflows and can be fine-tuned for different types of materials. So even though we have very good working method, we still facing with two challenges. The questions and the study is like how we can develop multi-slice data set which resembles polycrystalline materials with realistic grains. So even though we use multiple thickness and orientations, still we have only single crystal simulations. Now we are trying to develop polycrystalline simulations, but developing large data set for multi-slice simulations is a bit tricky. And next, how this is an ideal goal where how we can use reinforcement learning to reduce experiment time when we introduce this into real-time framework. So in the end, I would like to hear from you, how can our framework help identify your material discovery loop? And if you have complex sample diffraction data, maybe we can explore it together. And I would like to thank again my advisor and my research team. And on behalf of Sara, Shayan, and me, I would like to thank ASME leadership for this opportunity and invite Siavash to synthesize our presentations.
Thank you, Sara, Shayan, and Anvesh. Before reflecting on the questions, I am delighted to recognize Professor John Clear, the Dean of the Gallery College of Engineering, for attending this session. Well, you have here 3 talks about the use of AI in engineering. Sara highlighted the need for predictive analytics in dealing with data-driven problems in the oil and gas industry, manufacturing, and supply chain. She wanted to know from your experience in energy, oil and gas, or supply chain operations, what factors or disruptions most affect forecasting accuracy, such as demand fluctuations, supply instability, or policy changes. She also asked how could the transformer-based forecasting approach can help in your industry to manage uncertainty better and plan for sudden changes. Shayan highlighted the need for AI-driven methods to accelerate patient diagnosis, and he asked, do you have any available projects related to his research on developing machine learning algorithms? And are there any applications or ongoing projects where Shayan's proposed methods could be applied or integrated? Anvesh focused on applying deep learning for faster material structure identification, and he asked how can his framework help identify your new material structure, and he would like to hear more if you are working with complex sample diffraction data for further collaboration. Now I will invite our participants to respond to the questions posed by Sara, Shayan, and Anvesh. I would like to get as many people to participate as possible, so please keep your responses brief, and we start with Sara. So first question, from your experience, what factors or disruption most affect forecasting accuracy, such as demand fluctuation, supply instability, or policy changes, and how could the transformer-based forecasting can be applied in your industry to manage the uncertainty better? Please raise your hand. Okay, thank you, Dr. Clear. Please go ahead.
I'm not sure I'm doing this in the right order, but I actually have a different question for Sara. Should I wait for that or can I ask that now?
Actually, we have an open, we will open the Q&A session later.
Okay,
After.
I'll wait.
Yeah.
I'll wait. Thank you. Sorry.
Thank you so much. So do anyone want to address these questions specifically?
Yeah, I've got one for you, Siavash. I just couldn't figure out how to raise my hand. I'd say on this one that pops into my head with what we do, and again, I'll give a little background. So working at Halliburton Energy Services, I primarily work on hydraulic fracturing blenders. So think of it like a big margarita mixer that blends up whatever the desired fluid type is to go be pumped down into the wells. So one thing that we have is not every job is the same or even close to the same. So what happens in West Texas is entirely different than what happens in offshore Angola. So we have the similar equipment that's required to do these operations. But one thing that I've been kind of trying to lay some groundwork for internally with our company is, for example, if we have a centrifugal pump on this piece of equipment, there is a vast difference in the life we're seeing in different locations, and that's due to a variety of factors. The big ones being the amount of volume pumped through the pump, the type of chemicals pumped through the pump, if there's any solids like proppants in the pump, and then honestly, the biggest one is probably how the operator operates the pump. If they're efficient in that, and if they're keeping it around its best efficiency point, or if they're wildly outside of that. And again, being a service company and providing stimulation operations, these pumps have to operate from 0 to 100% all the time. So we're able to gather a lot of data from these, but it's never been put in a model to actually look at. Can we start to use that and begin to, let's see how I put it, begin to comprise or compress that data into something where we could start to predict maintenance on it and begin to have an equivalent metric of whatever it might be of gallon of fluid through each pump. What does that do to the life of it? So I think something like this could be, like I said, I've started kind of laying the groundwork for it, but watching these, I know there's a long way for me to go on learning in our neural networks and large language models to actually get some predictive maintenance working. But that's one place I definitely see this being helpful.
Yeah, thank you so much. Well, is there anyone else wants to address Sarah's question? Okay, great. Yes, please go ahead.
My the first thing that came to mind on that was the political policy changes, and all I could think of is good luck with figuring out how to tie that in.
Yeah. Yep.
Thank you so much. Well, let's proceed and responding to Shayan Shafaei's question. Do you have any available projects related to Shayan's research on developing machine learning algorithm? And are there any applications or ongoing projects where Shayan's proposed methods could be applied or integrated? So again, I would be happy to raise your hand and give your comments or responses to Shayan's. Yeah, thank you, Rodney. Please go ahead.
Yeah, thank you. So it's not necessarily in my field anymore, but I was thinking maybe this could be used in a similar way as for predictive maintenance in some way, into grouping certain machines into into classifications, into groups, into performing well based on the factors you're looking at, performance degrading and then failed, of course. Could you see it being used like that, Shayan?
We believe that in all of the classification area, we can use that. The healthcare is just a case study here, but yes, for all of the area which can categorize in the classification data, we can use that.
Thanks. Okay, great. Maybe we can continue the talk after this session with Rodney. And the next panelist, Anvesh, he asked, how can his framework help identify your new material structure? And he would like to hear more if you are working with complex sample diffraction data for any further collaboration.
Anvesh, I have a question. One of the things that I was looking at your graphics and your works around material structures, but the way that you've got your model built, one of the things that just leaped into my head was orbital debris analysis. Especially when you look at the graphics, it's if you take a macro view of when we're taking a slice of the sky in depth, I've just got this gut feeling that your work could be helpful in analyzing that, not only from a positional analysis perspective, but being able to dial into the peculiar behavior of particular patterns. So just something to consider.
That's great. Thank you so much. Yeah, so yeah, they developed similar models recently. They used LLMs to predict those kind of images, but processing them in point sets is much more. It makes more sense if you process them as point sets. Thank you so much.
I've got a question, and it's just a suggestion more than a question. So at OSU, our graduate material science and engineering program is physically located at OSU Tulsa. And we have a couple of faculty members there who might be interested in talking with you if you were to contact them first about whether they have applications for your method. One of them is Dr. Raj Singh, S-I-N-G-H, first name R-A-J, Dr. Raj Singh. He has recently been inducted into the National Academy of Engineering, so he is very well known, and he does work in material structure. So I'm going to suggest you might just contact him. You could use my name it might help him answer your email or your query. Again, Larry Hoberock, Hoberock. And another person who is also more on he works mainly in the composite side. I don't know whether you specifically mentioned your applications in crystalline type materials, but he may also be interested in discussing with you. And matter of fact, he's going to be our speaker in the last Thursday in January. He'll be a speaker on some of his work in primarily the composite materials applications, and he has a number of patents out. You might also try to contact him. His name is Dr. Ranji, R-A-N-J-I, Vaidyanathan, V-I-A-D-Y-A-N-A-T-H-A-N. And you can also use my name. Both of these guys will know me, and I don't have anything specifically to suggest in answering your questions, but maybe you can get some leads from those two.
Thank you so much. Those are very valuable recommendations. I'll definitely reach out, and thank you.
Okay, thank you all. I think it was great to hear your suggestions and advices to our panelists. It can help them to proceed in their academic journey for sure. And now we will open the question and answering session. Please raise your hand and ask your general question from our panelists, or you can even type in the chat and I will read it to our panelists. For sure, our speakers will be happy to receive your questions and comments which can help their research. First of all, I want to invite from Dr. Karishma. I know that in the UK it should be very late, like 1 a.m. So we would be happy to hear from you first, Dr. Karishma.
on a topic I'll know very little about. Thank you, Siavash, for putting me on the spot. I appreciate that because it makes me think. So this is what came to my mind when I heard about the X-ray diffraction data that Anvesh is doing. So Anvesh, my question to you is this. Given the limitations of requiring crystalline structure for X-ray diffraction, if a structure changes if a material changes its structure and starts becoming amorphous, it indicates its decline. For example, blades in an aerospace turbine, or indeed any turbine. Now, does your model potentially, therefore, have the capacity to predict the aging of a material and therefore the time at which it will fracture?
We generally didn't focus. That's very good question. Thank you. And we generally didn't focus on the mechanical properties, but still, once this model, mostly you don't need to think of it as a classification model. You can think of it as a representation model. Once you have representations, and if we can provide model some amorphous data also for fine tuning, once we get the representations, then we can do downstream tasks much more, like depending on maybe for the task you mentioned, we can assign particular downstream task model and get better results. It will take some time, but we can do it with right data and right definition of the task.
Thank you very much.
Thank you.
Thank you so much, Dr. Karishma. And next, Professor Clear.
Hi, my apologies for not being on video. It's not working on this computer. This is a question for Sara. It's a very general question, but I'm curious about, have you thought about applying your techniques to remote patient monitoring, where you might have, very high sort of spatial distribution of data, also temporal distributions?
Sara, could you please unmute yourself?
Thank you so much, Professor Clear. It's a really nice point that you brought up, because as I mentioned, I didn't implement in the healthcare with this use case that I used is supply chain, but that is the things that is really important point in healthcare as well, because transformer in 2007, for example, we said ChatGPT is G is for generative, pre-trained, T is for transformer. Why? Because transformer is basically in 2017 designed for natural language processing. But because of all the ability that it has, now it's implement in time series forecasting, even image recognition, in any kind of the domain. Why? Because it has one important point, self-attention. Based on the healthcare, you mentioned, yes, when the patient monitoring is changing all the data a lot, in this way, it allows the weight to assign the weight to the important different part. Is really essential, is really important feature, and because of that is getting more famous during this time, even it is newer model. And also one important thing is for patient, for example, monitoring, we have long series of the data that unlike of RNN, LSTM, transformer doing in parallel. So it would be the really great model to implement in healthcare domain. Unfortunately, I didn't go through it because just the way that I am doing is another domain that I am working. But because of all these features that I mentioned for transformer is for sure would be great idea to implement in this way.
Thank you very much. Appreciate it.
Thank you.
Thank you so much, Professor Clear. So Samuel will be the next.
Hi, I have a question for Shayan. So according to your results, there's a trade-off between speed and accuracy in some diagnoses. So my question is, do you think that the randomized WNN can be combined with another machine learning model in order to improve the accuracy? Because in the healthcare system, it's very important a balance between not just speed but also the accuracy of the results.
Thanks for your points. That's a very good question. We can use that in the other models, but the main point is that we have to change the setting of that. Since the base setting currently is just working on the k-nearest neighbor, since when we pick the compressed set, we try to pick the most effective one. What does it mean? It means it can correctly classify all of the training points, labeling them correctly without any error based on the training points with using the k-nearest neighbor. So assume that we want to use the logistic regression or in the more advanced using the neural network. We have to change the setting of that to be adaptive with the setting of that model. But yes, these days, the randomized learning is the hot topic to use in the different machine learning models.
Okay, thank you.
You're welcome.
Thank you, Samuel. So Roshan, you can unmute yourself and ask your question.
Yeah, my question is to Sarah. So in the presentation, you mentioned that the forecasting can be applied to policy. Tell me if my understanding is right or incorrect. So is it that like you look at a policy and see how these policies have affected changes in that specific area or the field, and based on those data points, you're able to predict, okay, what sort of policy changes would affect certain things in future? Is that what forecasting for policy changes would be, or is it other way around where you can predict the future state and say, okay, this is how the policy should change to achieve the future state?
Thank you so much, Roshan, for bringing this out. That's the point that you mentioned is regarding the work that I am doing in my PhD. The things that we are doing at this moment, predictive analytics is everywhere, and the people are doing, okay, predictive analytics, but there is one problem that they are predicted the data, but there is not a specific things that they will be able to convert this predicted data to the future, to the system, to the policy, to the any kind of the uncertainty that we have in the system. So one thing that we are doing predictive analytics and getting the data, considering as an input of our system, the way that we are doing, we said, okay, now we want to predict the behavior of the future of the system. Why? Because system is continuously changing. We are considering the evolving system, the system that is changing based on the time. So in this way, we are able, one thing that we are doing, converting this predicted data to different kind of the policy that we wanted to do. And it's not a specific, belong to a specific domain. We wanted to be able to generalizable in different kind of the domain. Thank you so much.
Thank you, Roshan. Anvesh, you raised your hand, so please go ahead.
Yeah, I have two questions, one for Shayan. So let's say, when you're working with matrices in deep learning, use KNN a lot. So like, can I borrow your model and use it anywhere I need KNN, like with?
Definitely, that's the main rule of that.
Okay.
Yeah,
Great.
you can use that in the larger scale matrix.
That's very cool. Thanks.
You're welcome.
And Sarah, I have a question for you. So when you mentioned the size of the data, you mentioned like some rows and columns. I understand the rows part. Coming to the columns, you have like maybe 130 or something your data set size, the matrices, the matrix size you mentioned. So each of that entry represents different aspect of the data set, right? How did you scale it, bring it to the same scale? And also when you mention the results, your results are like, you have normalized results and you have actual values. So were those actual values are renormalized, or did you train the model with those actual values? Because it will be very hard to train with that.
Yes, the things is based on the data when we want to talk about the complexity of the data, sometimes consider the data with around more than the 10 million data, we don't consider it as a complex data because just they arise the number. Arising the number, high number doesn't mean complexity. When we are talking about the complexity, as I mentioned, when our data is heterogeneous, that means we are combining different kind of the layer. They are not same like physical layer, social layer, economic layer, different kind of the layer. This will add complexity to the system. And another things regarding our data, since it belong to different position in the Puerto Rico, different geographic zone, the data were different. It was not same balance. That is one part regarding the complexity of the data, why we call it complex, not just because the number, yes, it was also based on the number because it was for 9 years gap, for 9 years, and the good point for transformer is good for long range dependency as well. You know this, I think, really well, that is the point regarding the transformer. And I got regarding the complexity, regarding the normalization.
Yeah, sorry. I don't, I don't have any question about data set. I just want to know how did you normalize your loss? And
regarding the normalization, I want to say everything is that we put it in the transformer, and for the data set that we have, all was the data for different years, but was connecting the cost of customer to different store. It was not really different layer of the data. To describe it, imagine you want to predict the price for house. There is different feature. One feature is number of room. One feature is a square feet. Absolutely, number of room would be 1 to 6, but a square feet would be around 4,000. In this way, you have to do normalize. Otherwise, you will lose one feature. But in our data set, we don't need to do this one because all the data was regarding the, for example, connecting cost, but it's different situation. But yes, finally, we did the normalization to be able to handle it better. And also the result that I showed was the number without the normalization and with normalization.
Yeah, thanks. Yeah, that's what I just want. Thank you so much. Because it's very hard to normalize the data.
Yes, you're right. Thank you for asking. And this is one of the benefits of transformer.
Yeah, thank you.
Okay, thank you so much, Anvesh, for your question. I think we can have still a few more questions. Okay, Dr. Karishma asked, in case this question helps, a question in general for all 3 speakers. Are you able to document the reasons for your model and making certain predictions or decision? Is your model open to reveal its decision-making analytical processes? I think we need to have very short responses from the 3 panelists if this question is going to address your research. We can start from Sara, then Shayan, then Anvesh. I'm not sure that is this related to your research at this point or not.
One thing is that I'm trying to read the question first, but one thing that I mentioned regarding she asked, is your model open to reveal its decision-making analytics? That is one thing that I am doing. Thank you so much, Dr. Karishma, for asking this. That is one thing that I am planning to doing in my PhD, that connecting the forecasting data for be able to do analyzing the decision making and all this stuff, decision making under uncertainty, because I wanted to say, yes, the system for the future, there is lots of uncertainty in the future of the system. So we are coming with defining several rules and also fallback rules to know how we wanted to deal with this kind of the uncertainty, and based on that, coming with the decision making. If I answer the question in my side. Thank you,
Thank
guys.
you. Thank you, Sara. And I think it can be considered as interpretable AI or machine learning algorithm to show how the method is going to be produced, the decision-making process, if I understood correctly. So Shayan and Anvesh, do you have any quick feedback and response?
Thanks for your question. In this, honestly, in my research, I try to address that, since all of the learning model trying to do the prediction. And in this case, I just talk about the KNN and the variant of that. So yes, it can use in the different prediction area, and it has a learning phase. So it can also use in different data set. The main condition is that we have to enough the data set to learn the model well. If we don't have enough data set, so the prediction of that wouldn't be good. Thank you.
Thank you, Shayan and Anvesh.
Yeah, thank you. That's very good question, Dr. Karishma. So we have, for my model, I'm kind of exploring two experts, like which experts were used by particular crystal system or particular lattice symmetry. So can we reveal it? And second thing, is there any trend in the attention graph we used? So like, is there any trend between different crystal systems or different thicknesses? Exactly, and different orientations. Does it make to change particular? Can it make any? Does it is it making some transition in the attention graph? And those are the two things we are studying. We are still working on it. I think we just finished this project very recently. So we will work on interpretability of this particular aspects. Thanks.
Thank you so much, Anvesh, Shayan, and Sara. I think we can have the last question from Andrew. Please go ahead.
Yeah, thank you, Siavash. Well, my question is to Sarah. Overall, the presentations were good. I learned several things. I was just curious to know why you used Puerto Rico as your case study for the data you used to train your model. And then since you did the forecast for 2015 from your presentation, did you get to compare the forecast with the actual data? I don't know if you showed that in the presentation, but I was just kind of curious to know how it compared to show the accuracy of your model.
Thank you so much, Andrew. It is a great question. Yes, why we select the Puerto Rico? Because the data for Puerto Rico was available for us to get the data for long term that we want. They had the data for demand forecasting. It was available, for example, for 2003, as I mentioned, until the 2013 that I got. And the main important point that you brought it up, yes, we got the data for 2015 because it was available. That is one of the reasons that, for example, it was able for us to go, for example, 2015 to 2020, for example, and predict the 2030, something like that, or 10 and predict 230. The reason that we come up with the 2015, because we wanted to ensure how accurate is our prediction. because we don't have the data, actual data for 2013 to be able to compare. But in this way, yes, unfortunately, because of the shortage time that we had, I was not able to show you the visualization, but yes, we did the visualization and we got a really good result based on also the visualization that we had based on the actual data for 2015 and our predicted data that we had for both of the data set. And since the data was available for long range that we wanted, we selected Puerto Rico.
Okay, that's good. So just like can you give a number of the accuracy of the model based on the comparison you did?
Sorry, I didn't hear you. Would you please repeat again?
Like based on your comparison, can you give a number for the accuracy of the model?
The accuracy was above 90, but I could look and send you the more information, or we already published a paper. Also, we would be really happy to share our paper with you.
Oh, nice. Okay, that's
Yes.
good. Thank you so much.
Thank you so much. Thank you.
Yeah.
Yes, that would be great.
Absolutely.
And sure, thank you everyone for participating today and helping our panelists to explore more on their research. And as a closing remark, I would say thank you, ASME leadership team, for the invitation to present, and appreciate all the GSC members who spent many hours coaching us, especially Professor Mistree. And now back to Isaac from ASME for closing comments. Thank you so much, everyone.
Yeah, thank you guys a lot. This event, that was a great event. These are always great events. We always enjoy the collaboration with OU and the graduate student community, get to learn a lot. Like I said, all this teaches me is that I've got a lot to learn. But I guess one quick plug would be, obviously we're the professional section and everybody in here is outside of undergrad, so try to stay plugged in. We've got the ASME section page that you can find that if you just go to ASME. I think if you just Google Oklahoma or Central Oklahoma section, it'll be there. All future events get posted on that. Similarly, the LinkedIn page, that one gets updated most commonly. We're also working on building the X or Twitter page and the Instagram. So if any of those are your preferred method, go ahead and give those a Google or look up, because like I said, any future events we have get posted there and we try to keep those up to date. Other than that, looking forward to the next one of these. Hopefully it's in person. We can all see each other again.
Thank you, guys. Great job. Appreciate your sharing your research with us. I learned a lot as well.
Great. Thank you.
Thank you so much.
Thank you so much. Bye.
See you all. Bye.
Thank you.
Bye.
Thank
Have
you.
a great evening.
Bye.
Bye.
Thank
Bye-bye,
you.
everyone.
Thank you,
Bye.
everyone. Have a great evening. Bye.
Bye.